This is the fifth in a series of videos that I'm making to support a course that I'm teaching in number theory. In the last video, we talked about the greatest common divisor. So let's recall that the greatest common divisor of two integers a, b, which we denote by the GCD of a and b, is equal to d if d divides a and d divides b. So that makes it a common divisor of a and b. And if c divides a and c divides b, then that implies that c divides d. So let's see. This means that if we have another common divisor, that common divisor must divide the greatest common divisor. So that means d is kind of like biggest in this ordering which involves divisibility. Then we also proved the following proposition, and that is for all non-zero integers a and b, there are integers x and y such that ax plus by equals GCD AB. In other words, the greatest common divisor can always be written as a linear combination of the two integers in question. We also proved some other results, but I'll let you guys check out that video if you need to. Okay, so let's start with the following lemma. So we want to suppose that a, b, and n are integers. And then we'll prove that the GCD of AB is the same thing as the GCD of A with B plus AN. Okay, so let's get to it. So let's maybe give these two numbers names. So we'll set D equal to the GCD of A and B. And then we'll set D prime equal to the GCD of A and B plus AN. Okay, great. But notice that means that D divides A and D divides B because it's a common divisor of A and B. But that means that A equals D times X and B equals D times Y for some integers X and Y. That's the definition of divisibility. Okay, so now where can we go from there? We probably want to look at something of this form, b plus an. So notice that b plus an is equal to dy plus dx times n. That's just from using this substitution right here and here for a and b, which we got because of this divisibility condition. But we can factor a d out of this, giving us d times the quantity y plus x times n. But the fact that we can write b plus an as d times some other integer is exactly what we need to say that d divides b plus an. Okay, great. So let's see what we've got at this point. We have d divides a and d divides b plus an. In other words, d is a common divisor of those two numbers. But d prime is the greatest common divisor, so that means that d must divide d prime. Again, by the fact that d prime is the greatest such divisor. Okay, so now let's work in the other direction. So we'll take this fact, d prime is equal to GCD of a with b plus an, to write a as d prime times x prime. And then similarly, we can write b plus an as d prime times y prime. Okay, again, that's because d prime divides a and d prime divides b plus an. I've just cut out this little step here, but that's pretty straightforward. Okay, so now we want to somehow achieve the number b because our goal is for d prime to divide b. So let's see how we can do that. Well, notice that b is the same thing as b plus an minus an, just by adding 0. But we know that b plus an is equal to d times y prime from this assumption right here. And then subtracting an is the same thing as subtracting d prime x prime n. Again, from this guy right here. But we can factor a d prime out of this, leaving us with d prime times y prime minus x prime n. Okay, but that means that D prime divides B. So let's see what we've got. We've got right here is saying that D prime divides A. Right here we see that D prime divides B. But that means that D prime divides the GCD of A and B, which we assumed to be D. And now we're ready to finish this off. Notice we have D divides D prime divides D, but those are both natural numbers because they're the GCD of two integers, and we take GCDs to always be natural numbers. So anytime you have mutual divisibility like this, it means the numbers are the same. So we have D equals D prime. But that's exactly what we wanted to show. Okay, so let's maybe get rid of this, and then we'll talk about a computational strategy for finding the greatest common divisor. Now we're going to look at a computational strategy for finding the greatest common divisor known as the Euclidean algorithm. So we want to start with two natural numbers a and b where b is bigger than a, although this can most assuredly be generalized to integers. And then successive applications of the division algorithm give us the following equations. So we've started by dividing b by a with quotient and remainder. So let's recall division algorithm says that b is equal to a times q1 plus r1, where that remainder is between 0 and a. Generally, you allow that remainder to be equal to 0, but here we're going to not allow that to be 0 because we're doing this successively and eventually the remainder is 0. So that means successive applications would stop immediately if the remainder is already 0. Okay, now we're going to continue this process. So we'll take a and then divide it by r1, that first remainder. So we've got a quotient of q2 and a remainder of r2. So r2 is between 0 and r1. And then we continue that until we get 0 as the remainder. So notice we've got r1 is divided by r2 with a quotient of 3, a remainder of r3, and then we've got this ordering on our remainder, all the way down to our very last step, which is the kth step in this process. And that says rk minus 1, or I should say it's the k plus first step in this process. We've got rk minus 1 is rk times qk plus 1. And that plus 1 is in the subscript there. There is no remainder here. So the first thing that we need to talk about when we're talking about this proof is how do we know that this sequence of applications of the division algorithm ends? How do we know that this is finite? That's actually not too hard, and that is because we have these strictly decreasing natural numbers r. So since we've got strictly decreasing natural numbers, maybe also including 0, and they're bounded above, well, then that means it has to terminate at some point. So that means we've got finitely many applications of this until we end with no remainder. Okay, so now we want to get to proving that, in fact, this last non-zero remainder, which I've called rk, is the GCD of A with B. Okay, so let's maybe see how we can do that. We'll do this by induction. And our induction will be built so that we follow this ladder down all the way to the bottom. Okay, so let's maybe start with our base case. So our base case will be the following statement, and that is that the GCD of A with B is equal to the GCD of A with B minus A times Q1. So that equality follows from the lemma that we just got done proving. But next, we'll see that B minus A times Q1 is exactly R1 from this equation right here. So we have this is equal to R1, which means we can write this as the GCD of A with R1. But now if we extend this up further this way, we can think about a as being our first remainder or our 0th remainder. So we might as well rename a R0. So that means what we really have is that the GCD of a and b is the same thing as the GCD of the 0th remainder and the first remainder. That sets up our base case. So like I said, our base case is writing the GCD of our goal object in terms of GCDs of remainders. So now let's go ahead and make an induction hypothesis. So we will suppose that the GCD of A and B is equal to the GCD of Rj with Rj plus 1. In other words, the GCD of successive remainders. And after making this induction hypothesis, we want to consider the next case. So let's consider the GCD of Rj plus 1 with Rj plus 2. So we hope that that's the same thing as the GCD of A with B. Okay, so where can we go from here? Well, we can use one of these equations to solve for Rj plus 2 in terms of lower terms. So notice this could solve Rk in terms of Rk minus 1 and Rk minus 2, just like this could solve R3 in terms of R2 and R1. So applying that, we see that we have the GCD of Rj plus 1 with, let's make sure we get the indices correct here. So we will have Rj, so that's like from this part that's on the left-hand side, minus Rj plus 1 times Qj plus 2. Okay, nice. Okay, so again, that's just from inverting one of these equations right here. Okay, but now applying our lemma, we know that this GCD is the same thing as the GCD of Rj plus 1 with Rj, because this right here is a multiple of Rj plus 1. But our induction hypothesis said that was the same thing as the GCD of A with B. Okay, so let's see what we've done. Our induction setup has proven that the GCD of A and B is always equal to the GCD of successive remainders. Well, that means that the GCD of A with B is the same thing as the GCD of the last two remainders. So that's going to be the GCD of Rk with Rk minus 1. So that's just, again, because Rk and Rk minus 1 are successive remainders. But this guy right here says that Rk minus 1 is a multiple of Rk. So anytime you have some setup like that, you know that the GCD is whichever one is dividing the other. So here we have the GCD is Rk. But that's exactly what we wanted to end up with. The GCD of A and B is Rk, the last non-zero remainder after doing this process. Okay, so let's maybe like clean up this theorem and then we'll look at some actual examples. Okay, now that we've proved the Euclidean algorithm works, let's use the Euclidean algorithm to find the GCD of 392 with 693. So an elementary school approach to finding the GCD of two numbers involves factoring them into primes and then doing something with that prime factorization. And that's fine, but in fact, factoring things into primes is very inefficient, whereas the Euclidean algorithm is very efficient. So if you were to put this into a computer would have an easier time doing this GCD calculation via the Euclidean algorithm rather than factoring into primes. Okay, so like I said, we're going to find the greatest common divisor of 392 and 693. So let's do that Euclidean algorithm. We need to take 693 and divide it by 392, keeping the quotient and remainder in mind. So this is 392 times 1 plus 301. So our first quotient is 1 and our first remainder is 301. Okay, from here, 392 will move over here and play the role of 693 in our last step. So let's move that here, 392, and we need to divide that by our previous remainder. So that's going to be 301. So that's how the roles are changing from one step to the other. Okay, but this is an easy division problem. Our quotient is 1, and then our remainder is 91. And now we continue this process. So 301 moves over here, 91 moves over here, and we need to write 301 as, let's see, it's 91 times 3, and now our remainder is 28. Okay, so keep going. So 91 moves over here, 28 moves over here, and we've got 91 is equal to 28 times 3 plus 7. Now you can already maybe see that this is going to be the last non-zero remainder, but let's just finish it off so that we know that. So I'm going to move this 28 over here, this 7 over here, and notice we can write 28 as 7 times 4. So that means we have this number right here, 7, as our last non-zero remainder. And by the proof of the Euclidean algorithm, we know that that is the GCD. So we have the GCD of these two numbers is equal to 7. So now you might want to answer the question, how can I write that GCD as a linear combination of 392 and 693? In other words, how can we do the expression described in this proposition? And that process is actually known as the extended Euclidean algorithm, and we're going to go over that now. So we start by taking each of these equations and inverting them in a sense. So let's do that. So we want to solve for the remainder. So here we have 301 is equal to 693. So I'm going to write that in green, minus 392 times 1. So I'll just leave that as 392. Then we'll do the same thing for all the rest of these. So I'll have 91 is equal to 392 minus 301, like that. So notice I've written my 693 and my 392 in green. We want to think about those kind of like variables here. Okay, now I'm going to solve here. That'll give me 28 is equal to 301 minus 91 times 3. And then finally down here, we have 7 is equal to 91 minus 28 times 3. And that's where I can stop, my last line where I have a remainder. So now from here, what I'll do is substitute from the top to the bottom until 7 is written as a linear combination of 693 and 392. So I'll start by taking this version of 301 and substituting it into the 301 that lives right there. So now we have this 91 is equal to 392 minus, so I'll put in parentheses, 693 minus 392, like that. Great. So I've just replaced 301 with what I saw before. Now I'll combine those like they're like terms. So let's see. That's going to give me 2 times 392 minus 693. And you'll forgive me, I'm running out of room there. But that's 693. Okay, now we're going to continue playing this game. So we'll take this value for 301, or I should say this expression for 301, and plug it down here. And then we'll take the following expression, which we just created for 91, and we'll plug it right here. And I just realized this should be in green. So I have minus 693. Okay, so let's see what that gives us. So that means we have 28 is equal to, well, that's 301. I wrote that as 693 minus 392, and then minus 3 times 91. So let's see, 91 was expressed like this. So we have 2 times 392 minus 693, like this. Now I think you can see where we're going. We're going to continue this process for one more step. So I'll take this value here for 28, plug it into this equation, and then I'll likewise take our previous expression for 91 and plug it into this equation as well. So let's maybe fast forward to what that gives us. Okay, so after all that substitution, we end up with the following calculation. So in the end, we have 7 is equal to 23 times 392 plus negative 13 times 693, expressing the GCD as a linear combination like we had over here. So here are some warm-up problems to try involving the Euclidean algorithm and the GCD. Turn these in if you're in my class. So the first is to find the GCD of a pair of numbers and then write that GCD as a linear combination like we did in our example. So the two pairs are 981 and 1234 and 6,660 and 19,980. So you'll do that for each of those. Next, I've got one which is a little bit harder, and that is to show that the GCD of a to the m minus 1 and a to the n minus 1 is the same as a to the GCD of mn minus 1. So here a, m, and n are all natural numbers. So you want to think about what you know about dividing polynomials for the trick here. Okay, that's a good place to stop.